have too much money, better if we could distribute it out to the poor, right?
Okay.
I said, I managed to ruin her entire worldview based on that, all right?
Okay.
Imagine for a moment you're at a company that has, where the distribution of money is that 70% of profits, revenue, go to the workers, 28% go towards material costs, 1% goes to the CEO, and 1% goes to the shareholders.
Okay.
Does that seem fair to you? And I'd say, yeah, it does. So imagine for a moment the company has 100,000 employees, each making an average of $20,000 a year. In this particular scenario, the CEO would make $28 million a year. However, if you were to distribute the CEO's wealth out to all those employees, they'd make less than $300 extra per year.
Okay.
In other words, it's a problem of scale.
Oh, that's not only scale, it's many, many, many things.
Yes.
And that's how reality works. I mean, I wasn't born in Russia, so I cannot speak for communism. That's the way I was taught, right?
There are ways we could attempt to, solve our problems, but economics is very complex, and you can't just redistribute because the entire point of economics is how do you solve the scarcity problem, and how do you solve the distribution problem? How do you ensure that the right resources get to the right people who need them, and do so in a way that's, moral and fair, so that nobody ends up getting shafted or working for free or anything like that.
Welcome to the problem.
I might need myself off mute.
Can
everybody hear me okay?
Hopefully this is the last thing of the semester. We don't have to deal with the CREDC meeting during Dead Week. Are we muted? No. Definitely. No?
Whoever just asked if you're muted, you are not muted. We can hear you loud and clear.
Muted.
I don't know that anyone.
Unmute your sister.
Maybe you're muted. Yeah.
You are.
Can someone on the phone please let us know if you can hear us?
Yes, I can hear you.
Thank you.
Thank you.
Okay, so announcements. The quarterly report will be due at the end of December. Due to the holiday break, we are going to be sending it out in early December. The format is going to be slightly different in an effort to make the quarterly report more efficient and more the liking of the DOE. If you're not muted yet, could you please mute yourself? We're trying to mute them from our end. The DOE has asked us to highlight specific projects, and in order to do that, we want to make the quarterly report more concise and make the information that they're looking for more easily found in the quarterly report. Therefore, the format is going to be slightly different. So we're going to send that out early for you guys. We highly suggest that you take advantage of the extra time that's going to be allotted to you. And if you have any questions, please utilize myself and Tricia as much as needed so that we can get that in on time. Because we will also have the annual report coming up quite quickly after that. Also, we will be doing an attendance every all-hands meeting just to see who's here.
And seminars.
And seminars, sorry. Who's here, who's participating. We want everybody participating. We need the feedback. Everybody benefits from that feedback. So here on site, we're passing around an attendance sheet. And those of you who are on calls, we're going to ask you to provide who is participating on your calls, whether that's a group call or you are participating on your calls individually. One last announcement. We do have a seminar coming up on December 11th, the Modernizing the Electric Grid, Enhancing Resilience in Cybersecurity with Juan Torres, the Associate Lab Director of Energy Systems Integration.
At NREL.
At NREL. Please, if you are available, make sure that you attend that. He is eager to talk to students. We've also set up a Google agenda sheet that you guys can sign up to speak to him as well. That was also already sent out, but if you need it sent to you again, please reach out to myself or Tricia as well.
And that's for on-site people, that we will have the seminar itself will be streamed, so we'll send out information regarding that once we have that set up from the technology team. And just to clarify for the quarterly report, it is due to the DOE and DOH January 31st. However, we need to have that ready much before that to have it reviewed. We will be sending out the form mid-December, and it will be due back completed the first or second week of January. So please allow plenty of time to accommodate that.
Can I add one more thing?
Yes.
So the attendance detail that Linda spoke of, this is not my rule or David Nichols' rule or anybody else's rule. This is a requirement as per the grant, and this will be enforced. Thank you.
Well, supposedly.
All right, so we are still getting some feedback from some of our callers. So again, if you have not muted yourself yet, please do so now.
The only person that should not be muted would be the presenter. Thank you.
With that said, I'm going to ask, let's see here.
This is Stuart Madnick.
WSU, who is on your call with you so I can jot that down on our attendance sheet?
So why don't we just have them send an email?
Okay.
Yeah, we don't need to.
Then you guys can send me an email. I'll message you actually here in just a minute.
If all the teams could just email Linda with your attendance, we'd appreciate it. Thank you. That's due by the end of the day today. Thank you.
All right, Stuart, I'm going to let you take over to do your introduction.
Very good. I'll be very brief. Hope you can hear me okay. It's a pleasure for me to introduce the upcoming speaker, Shaharyar Khan. He's a Master of Science student in our System Design and Management program here at MIT. He previously received a bachelor's degree in mechanical engineering from the University of Waterloo in Canada. But prior to joining MIT, he had to work in the operational technology industry, working as a lead site project engineer at an energy facility and as a design manager at BWX Technologies. He's a registered professional engineer in the province of Ontario, Canada. In his talk, he's going to explain what he's been working on, operationalize the use of system theoretic design approach to identify and mitigate cyber vulnerabilities in energy systems. Without any further ado, Shaharyar Khan.
Good afternoon. This is Shaharyar here. I thank you for the introduction, Professor. The topic of my presentation, as you explained, is identification and mitigation of cyber vulnerabilities in industrial control systems using a system theoretic design approach. Now, I want to motivate my talk based on my personal experience working in the field as a site project engineer at a major energy facility. And I've had the privilege of working both in design as well as in operations. And as many of you would already acknowledge, the time to react to emergent situations in operations is orders of magnitude less than in other business functions. I'm talking about 5 minutes to make a decision and move on, 15 minutes to, and if not, escalate it to your supervisor who has 15 minutes to resolve an issue. And if not, within 30 minutes, the problem has to be reported to the customer. So when faced with such pressure, time and time again, I've noticed, and I've personally have taken steps, and I've noticed my colleagues taking steps, which have jeopardized the integrity of the plant's air gap. Missteps, like connecting an unverified USB into the plant's HMI or into equipment that connects into the plant's HMI. And to give you maybe a brief example about this, in one particular operation, the machine that was running our SCADA system was an old Windows 95 machine, and one fine day during a critical outage, it stopped working. And so, one of the vendors actually, who was also responsible for the systems engineering of the project, had a machine whose origin was not really known, but was used, was a similar configuration and had been used for testing or making some prototype work or something else. And so, without asking any questions, that machine was shipped in outside of the site, of the plant site, and connected directly into the plant's control system. Now, I don't want to go into the specifics of the missteps over here, but these kinds of steps were appreciated by all levels of the hierarchy, or they were turned a blind eye to it because of the requirements of working in operations. And it is because you're saving time on critical path. So there's something more that's required that we have to think about in terms of what's causing these kinds of things. So you may think that this was just a case of poor training or bad bad culture, work culture, like the cartoon over here. But I would argue that this was a symptom of an ill-designed system. Now, the traditional approach to analyzing or identifying vulnerabilities in systems is to use analytic reduction. What that means is that you decompose a system into smaller components and analyze each component individually or piecewise, and then combine the results. And well, in doing so, we make a number of assumptions such as when the individual components do not interact in indirect ways. Assumptions like each event is a direct result of the preceding event, and so on and so forth. And these assumptions may hold for simple systems, but in our increasingly complex, software-intensive, socio-technical, tightly coupled systems, these assumptions don't hold. And therefore, there's a need for a new theoretical basis. And we believe that systems thinking can provide that. So formally, our research vision for this project is to develop software tools based on the systems theoretic design approach for operators to identify critical cyber vulnerabilities and mitigation strategies in energy systems. And we're basically following a two-step plan. We've made progress simultaneously on both steps. The first step is to ruggedize the actual approach, the method, by applying it to as many real-world use cases as we can by collaborating with industry partners and using real-world use cases. The second approach is to start deriving the lessons that we learn from that and converting them into functional requirements for software. And so my colleague, Taylor Andrews, has been actively working on developing software for this kind of analysis. But the presentation today will mostly focus on the first part of the plan. So what is the system theoretic view of cybersecurity? Well, to understand that, we have to understand what is systems thinking. So systems thinking is a way of viewing systems from a broad perspective that includes seeing overall structures, patterns, and cycles in systems, rather than focusing on individual events or components. Now, there are a few principles in systems theory. The first one is about interconnectedness. That means that every component is part of a system, which is part of a larger system, from an atom all the way up to the universe. The second idea is about loop thinking, which means that causality is an ongoing process with feedback influencing causal factors. This is different from the usual Swiss cheese model where causality is considered to be running in a single direction. Then we have the concept of emergence. Here, emergent property is a property that the system exhibits which the individual components do not exhibit. So, like a blackout on the grid or an instability on the power system would be an example of an emergent property. To give you an example closer to home, like a traffic jam on a highway would also be considered an emergent property. Now, we consider safety and security to be emergent properties of systems as well. The whole is greater than the sum of its parts. It's pretty self-explanatory. The fifth idea is about gaining knowledge about systems by combining things, by synthesizing components, rather than looking at the details of individual pieces. And finally, there's this concept of system mapping, or gaining knowledge about the system by understanding the ways in which it interacts with neighboring components and other components, and how the overall structure behaves. So to demonstrate these principles, we basically put a picture over here. This basically shows the interdependencies and interconnectedness of critical infrastructure. So, we're interested in electric power, and a lot of this is sometimes not really evident at the onset of an analysis. But this is exactly the kind of thinking and exactly the kind of research that we're most interested in. So, for instance, for electric power, we know that we need natural gas, but we sometimes forget that we also need water for cleaning and emissions reduction and cooling functions and those kinds of things. But at the same time, to run the pumps and the control systems and stuff for the water infrastructure, you need electric power. Similarly, you also need oil as backup for the gas supply. Similarly, but you also need fuel oil for lubricants and stuff to run your electric power systems. And the oil part is actually dependent on transportation, which in turn is dependent on telecommunication. So there's this complex web of interconnectivity, which sometimes we don't really consider when you're siloing ourselves into looking at just an individual component and analyzing it. So Professor Levison here at MIT basically came up with developed an accident causality model based on systems theory called STAMP. It stands for System Theoretic Accident Model and Processes. And it's basically, you know, the basic assumption is that accidents are not a result of individual component failures. Rather, they result as they're a result of loss of control. So it becomes a dynamic control problem rather than a failure prevention problem. Now, this is part of, her idea was to deal with safety. We consider cyber incidents to be a type of an accident or type of a loss. So our research is actually mostly focused on, on cyber security, on the cyber aspect of it. And, Professor Madnick, who's my advisor for this research, he often gives the example that, engineers are always trained to think about individual failures. They never really think about failures as static, as being independent. So, for instance, the probability of one pump failing would be X, but the probability of two pumps failing at the same time would be significantly less. But in the case of a cyber attack, you could have the same failure mode which caused the failure of one pump could cause the failure of all the pumps in your plant. So it's a shift in mindset. The other thing I want to mention over here is the STAMP accident causality model. So if you're operating at the symptoms level or the events level, if you're deriving your mitigation strategies at the events level, we're only really scratching the surface. We're only really in a position to react. For instance, a tradesman is found watching movies at 3 a.m. on a Sunday morning on the plant's HMI, and the reaction is to fire the guy for breaking procedure. But the problem, the question to ask is that why was he watching it? Was it boredom? Was it out of not having enough work? Interesting? Was the work not interesting enough? So there's deeper levels to it. So for instance, if we start looking at the patterns of behavior, patterns of events, we are in a better position to anticipate and respond. So remember, in the first case I said, if you're just looking at the events, you're reacting. If you start looking at the patterns of behavior, you're in a position to anticipate and respond. If you go further deeper and start understanding the structures that are driving the patterns which are causing the events, well, now you're in a position to start designing the system to prevent failures. And finally, if you understand the thinking that's leading to the structures, which is driving the patterns of behavior, which is causing the events, well, now we're in a position to transform the system. We're in a position to learn about the system and influence it properly. So like I said, and that's kind of where we're most interested in. We're most interested in the area where you're able to design and you're able to challenge the mental models and the basic assumptions that we're making. So, STAMP is basically a framework. It's a set of assumptions about how accidents happen. The actual analytical methods based on STAMP are called CAST and STPA, and there are others as well. CAST is backward-looking, so an event has already happened, and you're trying to understand what went wrong. STPA is forward-looking. When an accident, you're trying to hypothesize how a system may experience failure. And STPA-SEC is a specialization of STPA, which deals primarily with security. So remember we said that in the STAMP model, accidents are considered to be a dynamic control problem rather than a failure prevention problem. So the goal of the system, the goal of the STPA-SEC method is to design an effective control structure that enforces the system's security and safety constraints. Now, control is used rather loosely over here. Control could mean control through design, which could be interlocks, fail-safe design, etc. It could be through process and procedures, or it could be through social controls, such as regulatory, cultural, or insurance, etc. So now I want to talk a little bit, give you a little bit intro into the STPA-SEC methodology. It basically consists of 4 steps, and it's identical to the STPA methodology, So the 4 steps are define the purpose of the analysis, model the functional control structure, identify unsafe control actions, and identify loss scenarios. The difference is that STPASEC also considers malicious actions. And this requires, again, a shift in mindset between, looking only at security and considering cybersecurity. I have an example of how to apply this methodology to a simple system, but I'm going to skip over this in the interest of time. So coming to a use case, the MIT, like many universities and colleges across the United States, generates part of its own power. It has a 21 megawatt gas turbine, a heat recovery steam generator, a boiler, and a chiller plant. Upstream, it's connected to the New England grid to supplement power during peak demand. It's also connected to the gas utility via pipelines, and we have about a week's supply of fuel oil to run the turbine and the boilers if the gas pressure is low. And on the downstream side, there is the central utilities plant basically manages the electric distribution and heating and cooling of the buildings. So in all, this is really like a microcosm energy facility, even though, and we really wanted to select this project because we wanted it to be small enough so that we can wrap our hands around it and understand it. But the insights and the method that we apply is really applicable to larger facilities as well. For the purpose of this presentation, I'm going to focus on the electric distribution side, and in fact, I'm going to focus primarily on the gas turbine. And the reason for that is because I wanted to show some kinetic events as loss scenarios, and nothing better than a gas turbine, which has been frivolously described as a rotating blowtorch designed to run at the ragged edge of self-destruction. In passing, I also want to mention that we've been validating our assumptions and our analyses with industry partners, including Exxon, ENGIE, Schneider Electric, etc., to confirm generality of our analysis and gaining valuable feedback. So, coming to the method itself, the first step of the method is to define the purpose of the system. One key assumption that we make over here is that we assume that the system is already compromised, and then we ask the question, what is the goal or the mission of the system? What is the absolute worst that can happen to the system? And what is it that we're trying to protect? What are the critical functions that the system is performing? So we have some standard tools in our systems engineering toolbox. One of them is the system problem statement, which we use to define the purpose of the system. And in our case, it is to manage electricity supply to the MIT campus by controlling turbine output using a distributed control system. Next, we define some losses. Now, losses are unacceptable conditions from the stakeholders' perspective, such as dead dismemberment or injury to plant personnel, loss of equipment, lost power generation, etc. Next, we define hazards. These are system-level hazards. Hazards are system states that can result in a system loss under worst-case environmental conditions. So, for instance, operating the turbine beyond normal operational limits, or violating correct sequence of operation, these are the kinds of hazards which could result in the system-level losses we described earlier. To give you an example, if money was stolen out of your bank account, that would be a loss, quite literally. But if having a weak password is a system state, is a hazardous system state, which could result in a loss when money was stolen out of your bank account. So that's the difference between losses and hazards. So next we ask the question, but now that we have an understanding of the losses and hazards, we ask the question that what are the processes that are being controlled, which if not controlled would result in a system level loss. And so by asking that question, and then further asking the question that who is controlling that process, we come up with a basic control loop. Within this control loop, you can, every controller has a model of the process that it's controlling, and it uses this we call it the process model, and it uses this process model to give correct control actions through the control algorithm. Now, in humans, we call these process models mental models. So, the idea over here is that, this is a basic control loop. You can think of it as a Lego block. By recursively asking the question of who is controlling what, we can come up with a control structure. So the picture over here now shows a full, like the high-level control structure for the MIT Central Utilities Plant. As you can see, it shows the plant as an abstraction. Going up a level shows the DCS, the operators, the plant engineer, the utility, and all the way up to MIT's leadership and the government. Zooming into the gas turbine control, we see that the main the main modules within the gas turbine control are the protection system, the fuel affecting control system, startup and shutdown control, and auxiliary control. Further zooming in, we start looking at some details. We're looking into the process model and the control algorithm of the fuel control system. And this picture may look a little daunting at first, but it's really just showing that the turbine output is being controlled by modulating the gas flow to the combustion chamber. And there's a protection system which kicks in if anything out of the ordinary is sensed by the controller. It basically shuts off the gas supply. Now, one point worth mentioning over here is that we're considering functional architecture. So we're combining not only the technical automated controllers, but we're also combining the human operators, the engineers, the contractors, etc., in the same diagram. So this basically gives you a bird's eye view of the entire system, which was defined by the system problem statement earlier. The other thing is that just by analyzing the control structure, we can identify missing feedbacks, key areas where there may be additional feedbacks are required. But the main point is that this structure has to be the control structure has to be at a level of abstraction where you can see the big picture, but at the same time derive meaningful insights from the system. So the next step in the STPA-SEC method is to derive unsafe control actions. Well, how do we do that? Earlier we talked about the process model. So we start by looking at the inputs to the process model, right? But we don't stop over there, because in the physical environment itself is a communication media. So components can influence each other even if their control loops do not communicate electronically. To give you an example, like the flame temperature in a gas turbine is controlled, is indirectly calculated using thermodynamic principles and pressure and exhaust temperature. So it's these kinds of ideas which typically are sometimes missed by purely software engineers who don't work with cyber physical systems. The other thing to note here is that once we identify the process model variables, we enumerate all the possibilities, and we select a single control action from the controller and analyze if that control action under the various system states would be hazardous. So, for instance, in our particular case, we've selected the opening of the gas control valve, and then we say that under what system states would this action be unsafe. Now, it's important to understand is that control actions can be hazardous if they're provided at all, if the wrong control action is provided at the wrong time, if it is not provided, if it is provided too soon, too late, or out of order, or applied too long or stopped too soon. But by going through this process, we have like a complete way to basically analyze the entire system state and derive some key insights about the system. And by doing so, we abstract out some unsafe control actions, which I'm showing over here. And I'm just going to read out one of them. So it basically says that the fuel affecting control system opens the gas control valve when there is a sudden loss of load or generator fault driving the turbine to overspeed conditions. Now, the final step in the STPA method is to derive loss scenarios. The way to do this is we hypothesize a loss scenario based on an unsafe control action, and then basically go through look at the entire functional control structure and see how each of the different controllers could contribute to the issuance of this unsafe control action. Now, if you look at the control loop that's shown over here, you'd realize that there's really two types of causal scenarios that could occur. The first one is that an unsafe control action is provided by the controller. This could be a case where it's receiving incorrect feedback. Its process model is inconsistent or incorrect, or there's something wrong with here. The second type of causal factors relate to correct control actions provided by the controller, but not implemented correctly by the actuator or followed by the control process. In this case, maybe the controller, the control process is under the influence of a secondary controller, or which is overriding the control inputs from the main controller. Now, since we're interested in cybersecurity, we also have to consider malicious causal scenarios, such as command injection or manipulation, feedback injection, node availability, communication delays, and drops. So I'm going to present a few loss scenarios over here. The first one is a case where it's based on the UCA, where the gas turbine controller opens the gas control valve when there's a sudden loss of load or generator fault driving the turbine to overspeed conditions. Such an unsafe control action could hypothetically result in the following loss scenario: that the rotational speed of the turbine exceeds safe operating limits, causing the main shaft and impeller wheels to be pulled out by centrifugal force to catastrophic failure. Now, the way to work through this is to ask the question that how could the various controllers interact to cause such a loss scenario? In this particular case, we noticed that the management actually made a deliberate decision not to have a mechanical backup bolt assembly for overspeed, to check overspeed conditions. And they have good reasons for that. It's expensive to maintain, and running the turbine at elevated speeds for testing and stuff has its inherent risk. It's inherently risky. But the problem is that the operator really has about 50 milliseconds to react to an overspeed condition. So if a malicious actor was to cause a feedback delay to either the operator as well as the control system, while simultaneously resetting the trip points for the overspeed condition on the protective system, you have a condition where you would have a kinetic event where you would cause a loss due to overspeed conditions. The second scenario I want to consider is that of out of order operation. So typically, a gas turbine, if it notices a flame out condition, it basically shuts down the protective system. Basically shuts off fuel supply to the turbine. But in the case of a controlled fired shutdown, the control valve is actually gradually closed. The speed of the turbine is gradually reduced in order to reduce thermal fatigue and stresses and those kinds of things. So in this particular case, the protective system knows that there's going to be a flame out condition. It is expecting a flame out condition to occur. But if a malicious actor at this point were to basically cause the control valve to open after a flame out during a fired shutdown, then you would essentially have an accumulation of combustible gases, which could result in an explosion. Finally, the third scenario we're considering is the gas is based on the unsafe control action that the controller opens the gas control valve when operating at design temperature limits, leading to overfiring of the turbine. Now, in this case, the gas turbine typically works on 6 different control loops. It could either be working under speed or load control. It could be working under temperature control, acceleration control, startup shutdown control, or it could be working under manual control. But if the over temperature limits are reset on the turbine, and the process model is deceived into thinking that it's in one control loop when in reality it's working in a different control loop, then there's a case for overfiring the turbine. The point is that a similar kind of attack scenario was, was perpetrated at the Saudi industrial facility, which was publicly disclosed in December 2017, known as the Triton malware attack. In this particular case, the safety controllers were targeted by the malware, which basically shut down the plant and caused losses in terms of lost production and stuff, but it failed to cause any physical damage. But the intent of the attack was to basically disable the safety controllers and then cause conditions which would potentially lead to an explosion. So the overall objective of this exercise, as we earlier said, was to design the control structure in such a way that failures could be mitigated or eliminated, or hazards could be eliminated. So we start with defining new requirements at the technical layer. Now, so for instance, one of the requirements would be that your protective systems should have a safety, like a physical feature that prevents malicious reprogramming of the safety controller. Another technical requirement would be that to have a mechanical bolt assembly, and if that is not possible, to have a standalone electronic system where there's a speed pickup and that turns off that shuts off the turbine in case an overspeed condition is detected. And the third one is about a valve position indicator. Now, this would be a case where maybe a light comes on, or there's a visual reference that the operator can use to ensure that, to have better situational awareness of what position the valve is in. Now, these technical requirements are not really helpful if they're not backed by process changes or procedural changes at the operator or supervisory level. For instance, if like the controllers, if some safety controllers are installed, but the key is left out of convenience or for whatever reason, key is left into the safety controllers and it's left in the wrong mode, then it's no good. So there should be regular audits by the plant engineer to ensure that the keys are kept separate from the safety controllers. Similarly, the operator would have to update his procedures to ensure that when they're in a fire shutdown state, they have to make sure that the light comes on or the valve indicator correctly shows that the valve is closed when they're expecting it to close. And finally, to elaborate on this a little bit, like for instance, the safety controller I mentioned has to have a safety switch. When I used to work at a plant, at one time, the HMI actually shut down at 3 a.m. on a Sunday morning. For some reason, it had to be reset. But when it came back on, nobody knew the password. So the next morning, actually, we printed out the password to the HMI for the main control system and pasted it right on the operator's panel. And these kinds of things are quite normal in operations. It's a thinking that we're after. We're trying to address some of these latent issues in the systems and the structures that are driving these kinds of behaviors. So finally, like these kinds of changes, like the leadership also has to take on a leadership role and has to follow like maybe a change management process or something of the sort to ensure that all the safety controllers within the plant are replaced with the appropriate ones. And the plant engineers and other people are following the procedures as they're required to. So I've basically presented to you a whole set of new requirements that not only span the technical side of things, but also the operator side as well as the leadership side. So far I've shown the analysis for a single controller for a single control action. Imagine repeating the analysis for multiple controllers and multiple control actions. Well, this is the reason why we actually need a tool. And so we have been working actively on developing this tool. My colleague Taylor Andrews has been working quite diligently at coming up with developing the functional requirements and start coding it. And basically this tool enables operators to perform a rigorous vulnerability analysis in a structured and systematic manner. And there's some advanced features that we're after, which is to be able to formulate and visualize the control structure, in order to understand the context in which the system is operating, and to be able to zoom in and out of the various various levels of abstraction, and understand the key leverage points between that exist within the control structure. So these are some of the things that we're actively developing in our software. And finally, this software that we're developing also one of the features that we're trying to develop in it is to eliminate redundancy. So for instance, if an operator has gone through a particular system state and deemed it as a hazardous system state, then automatically, if that analysis is repeated, if a similar system state comes up again, it's marked as being hazardous. It doesn't have to go through it again. So in conclusion, we started with an understanding of systems thinking. We then moved on to understanding the goal or the mission of the system. And then we identified some of the critical functions for the system. And from there, we identified what are the control actions that that have the potential to move the system from a safe state to an unsafe state. And finally, we looked at the functional control structure and said, what are the types of interactions between different controllers that could result in the issuance of such unsafe control actions? Now, there are two key advantages of following this approach. One is that by following a top-down approach where you start with what is most important to you, or what is critical to the operation of your system, the analysis is more targeted and more strategic. And the second advantage is that by using the functional control structure, we basically have a bird's eye view of the entire system, which does not only include the technical side of it, but also the social as well as the managerial side of it. And so this is where we're at. We have been collaborating actively with our industry partners. We had a lot of interest during the CREDC conference, and we followed up with them, and there's been active engagement. And we want more of this. So if there's anybody in the audience who'd like to collaborate on this research, we'd like to welcome that, and we're looking for active collaboration in this area. With that, I'm at the end of my presentation. Thank you for hearing me out, and I'm open to questions.
Thank you very much. Does anyone on the call have any questions, or anyone in the room have any questions or any feedback? Grace?
Yes. Hi, thank you for the presentation. I really like this top-down systematic level approach. So my question is that how do you make sure that your tools are comprehensive? In particular, for example, for your step 2 of the TTA step tool that you need to model the functional control structure. So how do you ensure that the model covers all the possible control structure? Another example would be for step 3, you have to identify the unsafe control action. What if there are some control actions you didn't know they were unsafe, and you couldn't include that in the model?
Thank you for the question. So I think step 2 of the analysis, there's no right or wrong answer, right? It's basically it should be it's a step that is typically done in pairs, or like more than one person does the analysis, and it's really up to the analyst to determine what level of the abstraction is right for them. And so there's systems engineering is all about abstraction and decomposition and hierarchy. It's all about combining things and analyzing them in that way. So there's no real correct answer that would say that, okay, this is the only way you can do it. So two people could model it differently, but still come up with the same answers. As long as the point is that by using that abstraction, you have a greater chance completely, of completely analyzing all parts of it, because you're using abstraction. So in systems theory, I was taught in my school that there's this 7 plus or minus 2 rule. Basically, what it says is that at every level you should have a maximum of 7 boxes, black boxes, where you can put stuff in, and that way, as you go through the analysis, you can always relate yourself back to the starting box, which was where you started, and you can always decompose it, go into more details, but it should always be able to you should always be able to compress it back and then and then combine it into a single box. That's the first part. The second one is about the unsafe control action. So again, by using the context table, we essentially exhaust all the different system states. So because we consider all the process model variables that are feeding into the controller, and we analyze the controller based on so we first step back and we ask that, okay, what are the different system states that could potentially be unsafe in this particular control action, and then we see what are the process model variables that we need to we need to model, and then enumerate all possibilities, and then go through each one step by step and ensure that we mark it as hazardous or not hazardous. And once we have a set of those, then we derive the unsafe control actions from there. I don't know. I hope this answers your question.
This is Stu Madnick. I just want to add a bit more of a humble way of looking at it. I think in the medical profession, they talk about do no harm. Our view is make things better. So we hope to be as comprehensive as possible, but if we're identifying, resolving problems that otherwise wouldn't have been resolved, we hope we are making things better.
Yeah, thank you.
Does anyone else have any questions or feedback?
I have a simple question. Shaharyar, thank you for the presentation. You mentioned that the MIT generation facility. So are you actually using that as a pilot site?
Sorry, could you repeat the last part of it?
Are you using that as a pilot test site?
So the MIT, I'm sorry, the last part I still don't understand. I'm really sorry about that. Are you using it as a what site?
Shaharyar, I think he was asking, are we using MIT as an actual test site? I think the answer is
yes.
Yes.
That's
correct.
Right.
Okay, thank you. And you also mentioned that you have some interactions with some industry collaborators. What is the nature of that collaboration? Is it just you've had a few meetings with them, or are they more engaged?
So far, we've been engaging them by sending them our papers that we've written on this topic, and getting feedback. So primarily for now, we have received a lot of feedback from the MIT Central Utilities Plant people who have been actively, who've given us very good feedback. And only recently we've sent some of our papers to some of the industry folks we met at the CREDC conference in September, and we're still awaiting more interaction with them.
So those were the ones, the emails that I saw like last week or earlier this week?
That's right, but in addition to that, like this whole SCCA SEC method itself, we have been in touch with Exxon, ENGIE, Schneider Electric, who, some of these people have been attending our conferences and stuff earlier as well. So, we've been talking to them also.
Okay, and have they sort of given you direction in terms of how they see this as value, or what is their motivation? So far, it's been more like we're like, for instance, we had a Schneider Electric person actually ask more questions. So the questions included that, okay, can I integrate this with my safety system or not? Like, why do I need a new tool, and those kinds of questions. So, that kind of engagement is what we have. Okay, thank you.
But getting back to the question, I think the motivation is the whole motivation behind CREDC. These are organizations looking for ways to improve. And at the moment, they're trying to evaluate how this method might be applied in their organization.
Shaharyar, this is Shabir from Oregon National Lab. I have a question. In one of the scenarios you mentioned, the safety of protection systems are disabled. In reality, like the turbines and so forth are designed very much using those safety systems in order to from catastrophic issues. So are you assuming that everything is disabled in a sense and in using this approach to show all hazard type of scenario and how it can ultimately, destroy equipment and so forth?
That is correct, actually. So, many times there's a hybrid of new and old technologies that are used in plants. Mm-hmm. And that's why, we are starting with the assumption where we want to use the physics-based attack methods and elaborate on those and show where the vulnerabilities could exist. And then if a particular vulnerability does not exist because it's not possible because of the specific type of implementation, then that's very good. But if it does exist, then we are trying to identify the entire vulnerability surface.
Okay. Yeah, because my concern was more from the safety instruments, because safety instruments are designed in different scenario. The logic solvers are really the box that are, programmed in order to make sure the safeties are engaged based on the limits, hydraulic and mechanical limits of the equipment that is monitoring and controlling. So I just want to make sure that, we're not telling industry in a sense to say, okay, cyber attacks can do this. Triconics was really was a thing, but it really didn't do anything beyond the logic solver because the mechanical safeguards were already built in. There are manual safeguards where the controller, there is a physical people have to key in before the logic solver can even do adjustments.
Yeah, understood.
Yes, I just want to make sure that as we are, articulating this project, that is put down as a, layer of assumptions, to say, we are kind of looking at it in the all hazard perspective.
Understood. Okay, thank you.
Thanks.
Any other questions or feedback? Okay, Tricia has one last announcement before we go.
Just so you guys know, we do have with WebEx 25 slots to fill. If we go above that, people get kicked off. We are aware of this issue, which is why we'll probably be switching to Zoom in the near future, but we will need to continue with it through at least next week. So I apologize for any of the students that I got emails from that got kicked off. We are aware of it, so my apologies. If you can gather together and do a call in a group, that helps alleviate some of this. But going forward in 2019, we hope to have a different option. So thank you.
It's a good problem to have now.
It is a good problem to have.
All right, thank you for your presentation, and thanks everybody. Have a great afternoon. And next week's presentation is our last one of this year. So there you go.
Thank you.
Thank you.